Well, Professor Curtis Meyer is a professor of physics and science associate dean for research at Carnegie Mellon University. He earned his BS at Oregon State University and his PhD at the University of California at Berkeley. He then took a postdoctoral position at the University of Zurich, where he spent 6 years working on the crystal barrel experiment at CERN and the H1 experiment at Xi. He has a long history of studying baryons and mesons with particular emphasis on gluonic excitations. He was a member of the class experiment at Jefferson Lab and one of the founding members of the GLuEX experiment, for which he served as the spokesperson from 2007 until 2020. It's a great pleasure for us to receive you at LISHEP, Curtis. You have 30 minutes and feel free to start your talk.
Thank you for the invitation here. I'm actually Eugene Chudakov from Jefferson Lab, was supposed to give this, but due to some issues with Department of Energy politics, he wasn't able to do this, so he asked me to step in. So I'd like to tell you today about the GLuEX experiment at Jefferson Lab. Start with a little bit about Jefferson Lab and the GLuEX experiment, and then what we're doing is we're searching for exotic quantum number mesons. These are basically mesons that are believed to have an explicit gluonic degree of freedom. So the gluon contribute directly to the quantum numbers of the mesons. And this is somewhat related to, I think, the following talk, which will be on glue balls, which are another form of gluonic excitation. And we're looking for these in photoproduction. So a photon beam on a proton target, and I'll talk a little bit about that and why that's an interesting way to search for these. And then how we're searching for these exotic quantum number particles in the detector, where the status of the searches are, and so forth. And then a little bit of interesting stuff on the end on JPSI photoproduction at threshold, which is a result that we published about a year ago that's gotten a lot of interest. So let me start with Jefferson Lab. Jefferson Lab is located in Newport News, Virginia, which is a little bit south of Washington, D.C. There's New York City, Philadelphia. And this is an aerial view of the accelerator. It's a 12 GeV electron accelerator in sort of a racetrack design. The electrons go around the path here, and they can go around up to 5.5 passes. You can get 5 passes extracted for 3 holes A, B, and C here. So it's a 12 GeV beam. You can get a 2.2, 4.4, 6.6, etc. in these holes. And then there's 1 extra half passive acceleration into hole D, where the GLuEX detector is. And we've configured GLuEX so that we basically only get photons in the hall. So we convert the electron beam through Bremsstrahlung into a photon beam. And we're using linearly polarized photons with about 9 GeV of energy. So this is the sort of the layout here. And the other halls have both electrons, and they can produce photon beams, but not the quality that we have in hall D here. And with hall D, we can only take the highest energy electrons that the accelerator produces. So when GLuEX, we're searching for, and there we go. Searching for hybrid mesons, which I said are gluonic degrees of freedom, and they're predicted by lattice QCD to exist, that these things are there, and there's actually ways to tell from the lattice when you found them that I'll talk about. And we're using linearly polarized approximately 9 GeV photons. And 9 GeV, that may seem low energy, but it's actually sort of optimized for the photoproduction of mesons in some sort of diagram where the photon comes in, interacts with the proton. And there's a lot of different exchange mechanisms that I'll talk about that are possible for low energy. If you get to very high energy, you're almost totally focused on one thing, which is Palmaron exchange. But here we have a lot of different exchanges to produce some particle X and then reconstruct that particle. This 9 GeV regime is an unexplored regime. There's almost, prior to GLuEX, there was almost no experimental data in this particular regime. So it's sort of open place to look if you can really get a high statistics experiment. And we've built a hermetic detector so that we can basically reconstruct exclusive final states. And the detector shown here, the electron beam comes in, it's converted to a photon, which I'll talk about in a second. Those photons interact in a liquid hydrogen target. There is a timing counter around them. There's charge tracking, cylindrical chambers, and forward tracking. This all lives in a 1.5 Tesla solenoid magnet. There's calorimetry in the barrel region here around the tracking, and there's another calorimeter downstream. and a timing detector downstream for doing particle identification. And since beginning of 2020, we've had a forward kaon system, which is a Dirk detector, which was actually recycled from the Bavar experiment at SLAC. But the data that I'm presenting today was taken prior to the installation of the Dirk. And we've, to date, with the initial studies of GLuEX, we've collected 125 inverse picobars of data that I'll be talking about today. There's more than a second sample that's larger than that, that's part of our running with the Dirk that isn't fully analyzed yet. So, but that's sort of the scale of the data set. So the photon beam is an important part of this. It's linearly polarized. We do that through a process called coherent Bremsstrahlung. So in coherent Bremsstrahlung, the electron beams come and they pass through a 50 micron thick diamond radiator. And by aligning the inverse lattice vectors of the diamond with the beam, you can produce a coherent Bremsstrahlung. And in coherent Bremsstrahlung, two things happen. The photons go pretty much straight down the beam line, and you produce linear polarization. And the degree of linear polarization gets larger the farther you get from the endpoint. And so we've picked sort of a regime 8.2 to 8.8 GeV, which gives us about 30% polarization. What we do, that the electron that produces the photon is then bent in a tagging magnet, and we basically, with a hodoscope, we determine what its momentum was, and that tells us then what the energy of the photon is. In addition to the coherent Bremsstrahlung, there's regular Bremsstrahlung that is unpolarized, and that actually comes out in a conical pattern around the beam. So we go 75 meters downstream and then go through a 5 millimeter diameter collimator, and that scrapes off a lot of the cone that's expanding from the unpolarized beam, and we basically get the coherent peak going through and into the detector. Once it's gone through that collimator, we have a pair spectrometer, which we use to measure the flux of the beam next to the detector. And there's a triplet polarimeter that looks at scattering off of an atomic electron to produce a pair, which then we can measure the polarization of the photon beam. And then the photon beam goes into the detector, and those that don't interact are dumped downstream. The linear polarization is a function of the beam energy, as shown here. This is measured, and so we take this region here, which is about 33% linear polarization. And you'll notice we have 4 different orientations. It's 2 pairs of orthogonal orientations. A lot of the measurements you want an orthogonal set, so say perpendicular and parallel to the floor, is 1. But to control systematics, we take a second set where we've rotated things by 45 degrees. So there's basically 4 polarizations that we take all the data in, and they're all analyzed together, but it helps control the systematics. And we use, like I said, we have linearly polarized photons. That does a couple of things for us. It acts as a filter on the naturality of the exchange mechanism, so it tells us something about what's being exchanged here. And the photon beams are unique in that they're spin 1. So sort of through vector meson dominance, they fluctuate into a spin 1 quark-antiquark pair, which is a rho, omega, or phi meson, and then that interacts with the proton target. So, and that's the sort of the unique thing. And then the addition, there's basically no data, or there was no data in this regime prior to GLuEX. Okay. So we're trying to look for mesons in the that have a gluonic degree of freedom. So we need to initially look at what are mesons. Well, they're quark-antiquark pairs, and the quarks and the antiquarks are spin 1/2 objects. So you can take 2 spin 1/2 objects and combine them together to form spin 0 or spin 1. So you see that here. You can also add orbital angular momentum L to the quark-antiquark pair, so 0, 1, 2, and 3, and that gives you a total angular momentum J, which is the L plus S. And the J is a conserved quantum number in strong interaction. So that's an important quantity. There's a couple of other things that are important when we're talking about the spectroscopy here. They're basically symmetries of the strong interaction. One of them is parity, which is a spatial reflection, and it's related to the orbital angular momentum. For just 2 particles, the YLMs basically go like -1 to the L. But because we have a quark and an antiquark, there's an extra factor of -1 in the overall parity of the system. And then there's another one where you turn the quarks into their antiquarks. So there's this C parity, which is given in terms of -1 to the L plus S. And that gives us a set of quantum numbers, J, P, and C, that are conserved by the strong interaction. And those quantum numbers characterize the non-nets of the mesons. You can sort of see that here. We take an L equals 0, S equals 0, JPC is 0 minus plus. That corresponds to the pseudoscalar mesons, the pi, the eta prime, and the kaons that we're familiar with. And you can keep building these up with L's and S's, and you build up this tower of JPCs that correspond to non-nets of mesons, the 1 minus minus or the vectors, the rho, omega, phi, k stars, and then you get up into sort of an alphabet soup of mesons going higher. And if you look at this carefully, you'll notice that there are several of these JPC combinations that aren't listed here. Those are known as exotic, 0 minus minus, 0 plus minus, 1 minus plus, 2 plus minus, and so forth. And if you find something that has those quantum numbers, it can't be a simple QQ bar system. So that's an interesting thing to look for, because if you do find something there, it's something that's not basically a simple meson. It doesn't tell you what it is, but it's not just a simple meson. Lattice QCD can also calculate the spectrum of light quark mesons made of up, down, and strange quarks and their antiquarks. And they do that in their JPC here. So here's the 0 minus plus, the pseudoscalars, the 1 minus minus, the vectors. These are negative parity and positive parity states. And this is showing the I equals 0 and I equals 1. The kaons aren't here, although those have been calculated. And so the I equals 0, there are two states, and you can characterize them as an SS bar state, which is colored in green, or one that's light quark state U and D, which is colored in black. And some of the non-nets have these mixed and some of them don't. So there's a mixing angle between these. And then there's the isospin 1 states as well, like the pi, the rho, and so forth. So this is the spectrum calculated by lattice QCD. And if you go over here, there are a number of particles that have these exotic quantum numbers that are also predicted to be here. And one thing you can do when you've got lattice QCD is you can go in and look at the operators that form these. So there's sort of a lightest set that they pick out, and the ones shown in brown here correspond to those, and those all have very large gluonic component, whereas the other ones here don't. The rest of the ones in the exotics do as well, but you can identify mesons that have a large gluonic component to them from lattice QCD. And so that's what we would call an exotic hybrid meson. There are those there. And again, focus in on that spectrum. Here's that blown up. There's the color again, showing the mixing, and the mixing angles are given here. And there's basically one non-net of spin 0, two non-nets with spin 1, and two non-nets with spin 2. And the lattice QCD, if you look at this and you try to model it like the quark model things, it's consistent. The gluonic degree of freedom is consistent with something behaving with JPC 1 plus minus, with a mass between 1 and 1.5 GeV over C. And experimentally, the only thing we have any experimental evidence of is something that's consistent with this state here, this isospin 1 state known as the pi 1 1600. It's not, experimentally, we don't know if it's one of these states or not. It's just consistent with that. And it's been reported in a number of experiments. The best results to date are from COMPASS at CERN, looking in eta prime pi and eta pi, but various other experiments going back several decades. And COMPASS, I'll show you some of their data later, basically published a very detailed study of the eta pi and eta prime pi final state and published the partial waves. And then the Joint Physics Analysis Center, the theorists at Jefferson Lab, analyzed that and basically pulled out the best measurement yet of this pi 1 1600, its mass and width. But that's the pi 1. I don't know what that is. That's this state. Where's everything else that should have been there? The other non-nets, and there's multiple in the spin 1 and spin 2. But these sort of particles here, which have these names, pi 1, eta 1 prime for spin 1, or B's and H's for spin 0 and 2. And if you look at these things and you think about photo production, you just sort of sit down and look at the possible things. With simple exchange particles of pi, eta, rho, omega, pomeron, B1 or H1, it's in principle possible to photoproduce all of these. That doesn't mean it's going to happen, but the quantum numbers work out that you could, through one of these simple mechanisms, produce all of these. So you want access to as many of these mechanisms as you can, and that's one of the reasons why we have 9 GeV photons. In terms of how these things decay, lattice QCD very recently, in fact this year, makes a prediction for the one state that's known, the pi 1, and they say the decay mode into B1 pi is dominant. And and much smaller rates into other final states, but they say nothing about the other ones here. And as I said, this pi1, the best data is actually on this eta prime pi, but there's been reports in all of these other modes as well. So, but then you'd like to say, well, where should you look for these other states? Because that's really what you need to map out. And that gives you this sort of alphabet soup of things here that are various decays. So here's the various particles, the exotics that I've listed here. And then there's various combinations of what they can, pairs of particles they could decay into. So here's pi rho, pi b1, pi f1, pi eta, and eta prime for the pi1. And a couple things just to pull out of this, because it really looks like gibberish here. But the red ones are the ones that are probably the easiest to do. So they're sort of the first searches that we're executing now in GLuEX with the data that we have, shown in red. And if you look, with the exception of this, which is two pseudoscalars, the rest of these are a vector and a pseudoscalar meson. With more data as we go forward and a little more development in the analysis, these blue channels become possible to search in, and the black ones are just difficult. So strategy to move forward is to start looking in the red channels for hopefully evidence for these unobserved exotic mesons, and then move to more to other channels as we get the data. So we really don't have predictions for what these can decay to. These are just what would technically be allowed through quantum numbers. So how we're going to do this? So first thing we want to do is we have this diagram here where the photon comes in, there's something exchanged. So we need to understand what the production mechanisms that happen in photo production and our energies are. And the linear polarization lets us learn something about, do we have natural or unnatural parity exchanges? Something about the exchange here, natural or 0 plus, 1 minus, or 2 plus for JP for the exchange, and unnatural are here. And that's why you want linear polarization. And then there are various measurements that we can make, which are beam asymmetries, which are differences between two orthogonal polarizations. Essentially the polarization of mesons that have non-zero spin density matrix elements. Some of those are measured for the vector mesons and so forth. And then we'd also like to so that's the production. We need to understand our acceptance. So these SDMEs require understanding the acceptance as well as cross sections. And then you want to start by reproducing known results. So what do you know about in various things that's published? Can you reproduce well-known mesons? And really the key thing, understanding this exchange mechanism here, simplifies the resulting amplitude analysis that we're doing by effectively a factor of 2 in terms of complexity. So it's an important thing to have. So let me just start with beam asymmetries. Like I said, beam asymmetries, you basically measure a cross section for the linear polarization, say parallel to the Earth minus perpendicular over the sum. So it's just two orthogonal combinations. You measure that in bins of T and so forth. And those cross sections are related to yields that are functions of the beam asymmetry angle, the photon polarization. And it's related to this beam asymmetry and connected to the linear polarization, degree of linear polarization. And it's got a phi distribution in the azimuthal angle. So they're measured this way. And if you look at these as a process here where you exchange something, and if that exchange particle it's natural, like 1 minus omega or rho, the beam asymmetry is 1. And if it's purely unnatural, it's -1. And so a couple of our early measurements where we did pi naught photo production, the beam asymmetry, you can see the GLuEX data here in black compared to old SLAC data, is all very close to 1. This is for the eta meson here, which had never been measured before. There's 2 GLuEX measurements, but again, it's consistent with 1 for a while and then maybe dropping off at larger momentum transfer. But it looks like the natural parity exchange is the dominant feature here, especially at low T. If you go to something else where you photo produce the pi minus against the delta plus plus, then something interesting happens. You start out with a negative beam asymmetry, so the unnatural is winning. And then as you go to higher T, the natural takes over. So this is probably pion exchange converting to something else as we go to higher T. So this beam asymmetry has let us learn something about what's going on with these production mechanisms. The next thing we can measure are the spin density matrix elements of vector mesons, which basically describe the polarization of those mesons. And 9 real elements can be measured. There's this postage stamp diagram below. It shows those, and not really worth going into them. but combinations of these can tell us something. So there's a parity asymmetry, which is the difference of two of these. And again, if the parity asymmetry is 1, it's connected to natural parity exchange, and -1, it's connected to unnatural parity exchange. And for the photo production of the row meson here, where the GLuEX data is shown in red, the old SLAC data is shown in green, you can see that it's very, very close to 1. So the natural parity exchange is sort of dominant. The omega is a little bit different. Again, the GLuEX data in red, the only existing SLAC data is a single point here. It's positive, but it's not 1. It's less than 1. And that's, again, probably due to the pion exchange in these. So measuring these spin density matrix elements is sort of an important thing. And we really nail these in a lot of different channels. So rho omega phi, we're publishing on excited baryon on the lambda 1520 shortly. But there are things that, again, let us get at the exchange mechanisms, but also demonstrate that we understand the acceptance of the detector. So now we move into the search for these exotic particles. And clearly the place to start is where there is evidence of something, the pi 1 1600 that I mentioned earlier, which Compass reported as seeing an exotic signal, or exotic quantum number 1- in the eta prime pi final state. And they published a coupled analysis of the eta pi minus final state and the eta prime pi minus final state. The two distributions are shown here. Here's the mass of the eta pi minus or the eta prime pi minus against a decay angle of the eta pi system, cosine theta Godfrey-Jackson. And you can see here, here's the pi. If you look in the eta prime system, you can see there's sort of a forward-backward asymmetry in the cosine theta Godfrey-Jackson. And the only way you can get that asymmetry is if you have an odd partial wave, and an odd partial wave corresponds to an exotic quantum number. So you can see that there has to be an exotic quantum number contribution to the eta prime channel here, and you don't see that in the eta channel. And as I said before, JPAC extracted from this published data the pole position of this, and then from this coupled data, there's actually 3 resonances that come out. There's the well-known A2 1320, its first radial excitation, the A2 1700, and this exotic state, the pi 1 1600, with the mass and width is reported here. You can look at the same things in GLuEX. So here's the eta pi and the eta prime pi. This is eta pi 0 and eta prime pi 0 in GLuEX. And in the eta pi, you can see a couple of resonances, the A0 and the A2. It's harder to see something here. And we can also in GLuEX, we don't have to just look for we can look for multiple decay modes of the eta to 2 gamma or pi plus, pi minus, pi naught to make sure we get the same thing. We can also do the charge exchange, so we can do pi minus off of a delta plus plus, and we're looking at all of these concurrently. There's a couple of obvious features, particularly up here, this band at very forward cosine theta Godfrey-Jackson. And that's something that we're trying to get a good theoretical grip on, and that's where we're working closely with the JPAC theorists to develop models to describe that. It has to do with something that historically is known as a deck effect, but it's related to something that's a double Reggie production mechanism, and it's present in both of these. But to do the partial wave analysis correctly and get the physics right, we need to understand that. And so the close collaboration with theory to get those tools right is ongoing right now. We can start by doing an amplitude analysis of this and look at this where we know what things are in the eta pi. So the A0 980 and the A2 1320. So we can include a small set of partial waves. It includes S and D waves here. And you can fit, there's a large S wave contribution, which is the A0 plus something that's extending underneath here. And then there's a D wave contribution, which is the A2. And it's interesting, it's only populating the M equals +2 magnetic substate of that spin 2 system. And that's actually consistent with things that have been observed in 2-photon production mechanisms. So there's an interesting carryover between photoproduction and 2-photon production with the A2. And this is still being studied, but we're doing these partial wave analyses here. The next thing we can do is, I mentioned earlier, so the other early interesting results were vector pseudoscalar decays or final states. And so K star K, omega pi, rho eta, rho pi, omega eta, phi pi. So understanding those is important. And one way to develop the analysis tools on something you understand is to find something that decays to that. And the B1-1235, its dominant decay mode is to omega pi naught. And so we try to study the B1-1235 in GLuEX in this decay mode where the omega goes to pi plus, pi minus, pi naught. So you can select the omega in pi plus, pi minus, pi naught, and you have sidebands for subtraction. And then you look at this here, and this large peak here is the B1 going to omega pi. This is about 20% of our data. And then you select a bin near the peak of the B1 to do a partial wave analysis and to try to make sure that what you're seeing is the B1 in there. When we do that, and we take this narrow bin and then we bin it in several bins of T's, there's 5 angles that describe this decay distribution, and the data those angles are shown in black. And the overall fit, which includes the B1 and also a row partial wave, is shown in green, and that's made up of 2 partial waves, the blue one for the B1 and the red one for the row, and these interfere, so they're coherent. So you can have things with the blue and red add up to something less than one or the other. But so that we're doing a reasonable job of describing the data here with the data and the green curve agreeing very well. So this is basically the mechanism for analyzing vector pseudoscalar final states on a well-known final state that once we've understood this, we can then move and do those other ones in higher mass. In fact, going up to higher mass and just in omega pi is already interesting because there's exotics there, supposedly. The other thing we can do is there's something known as a D to S ratio. When the B1 decays, it can decay through an S wave, an L equals 0, or through a D wave, L equals 2. There's been a lot of measurements of these over the past. There's a lattice prediction here shown, and then this is the predicted measurement that we will be able to make with the uncertainty from GLuEX. So an interesting result here that we can pull out with this. Like I said, there's other channels, the other vector pseudoscalar that we will look at. And we've already looked at a number of these, and not unexpected, but there are no narrow structures observed in the interesting MASH region for the exotics, which is around 2 GeV. So we need to do a partial wave analysis to search for broad states, but that's building up the tools right now to do that. So that's forthcoming. Call this opportunistic physics now, which is the J-psi photo production at threshold. So basically, in GLuEX, the photon comes in, you photoproduce a J-psi, the J-psi decays to E plus, E minus, and there's a proton that comes off. So the E plus, E minus these are detected in the calorimeter, requiring the energy and momentum to be the same. And we can reconstruct this for the full phase 1 data set. And here's the J-psi signal, a little over 2,000 J-psis. This is the phi meson. And then the background here is a beta-Heitler process that's used to normalize this. This is interesting because it's a result from LHCb that came out in, there was a first one that came out a few years before this, but the most recent in 2019, where they observed particles decaying into J-psi proton, which would be a pentaquark type state. So they actually observe in the J-psi proton invariant mass 3 narrow peaks here, which are these P sub C states produced from lambda B decay. And what's interesting is these states here, if they're tightly bound states, they should in principle be able to be photoproduced through some S-channel production process. So the photon comes in, fluctuates to a J-psi, interacts with a proton, forms a pentaquark, and then decays. So we could look for this in GLuEX. And if you look at the threshold region, photon energy versus cross-section, the data prior to GLuEX, this is from SLAC, this is from Cornell, where these arrows are where those 3 states would show up against the photon energy. So they're well within the regime that we could measure with GLuEX, which is this shaded region here. So we have an initial publication here in 2019 where we published about a quarter of the statistics, not quite 500 events, 27% normalization uncertainty. But we were able to, we can look for the LHCb pentaquark, and that cross section is shown here. The GLuEX data are in black, the old SLAC data in red, the Cornell data in blue. And this is what a pentaquark would look like on that data, so you don't see anything obvious there. But there are some other interesting things as well that go into here. This cross section, there are various curves on here. When we went into this, there was a discussion about these two curves here, which involve are two gluons or three gluons involved in the production process of JPSI at threshold. And what it looks like is when you're very close to threshold, the three gluon process is important, and then the two gluon takes over in that sort of picture. And there are other models as well that describe this, but and then by looking for bumps in this, we were able to set upper limits on branching ratios of basically the pentaquark to JPSI proton for the various states in LHCb. We didn't see anything, but we could set upper limits. This result also generated, yep.
3 minutes, Professor.
Okay, I'm very close here, so thank you. I think we're good. So this also has generated a lot of theoretical interest. There's a result here where basically they're trying to compute the mass radius for the proton. So where's the mass radius? And it's quite different from the charge radius from this fit. And that's just the JPSI data. But to get these error bars smaller on the data, we need more data near threshold, which we have. There's also people that have looked at this in terms of open charm. So that these sort of, if we go back and look at the GLuEX data, it comes up, goes down, and comes up here. Focusing in on that, comes up, goes down, goes up. Those little blips or jumps here correspond to open charm threshold. And so this paper says that most of this cross-section is due to open charm. So these two pictures are incompatible theoretically, but they both are interesting here. And basically higher precision data is needed really to understand this. And that's what we're in the process of publishing our larger data set, and then there'll be an even larger one coming from the phase 2 of our data. So let me go ahead and summarize here. So our phase 1 GLuEX data, 125 inverse picobarns, we're analyzing it. We're starting to carry out some of the critical analyses to look for exotic hybrid mesons, and we're excited to get about a factor of 5 that statistics ultimately with improved K-on identification in the forward region with this DIRC. We've done measurements, the beam asymmetry, to allow us to start looking at production mechanisms of simple final states and see what seems to be important in photo production. Similarly, spin density matrix elements allow us to study more complicated production. And we're carrying out some of the initial searches on eta and eta prime pi, which is the first probably key exotic search, and building the analysis tools that will allow us to follow on with the vector pseudoscalar final states. And then we have very interesting results on JPSI photo production. So thank you for your time. And our sort of standard acknowledgements is you want to scan the URL code with your phone, you'll take into a site where we acknowledge all of our sponsors. So thank you.
Thank you, Professor Curtis, for providing an excellent overview on the status and perspectives of GLuEX experiment. So we have time for one question. I don't see any question here. I have
a question.
Okay, Professor Santoro.
Yes.
Okay, Curtis, what about the radiative decays from JPSI and others, and also a number of announced global candidates since a long time? They need to have partial wave analysis too to define. Do you agree?
I'm sorry, I missed what the question was.
If you agree that they need to do the partial wave analysis.
You absolutely need a partial wave analysis to pull out the quantum numbers. Yeah.
Okay. And about the radiative decay from JPSI, for example, forbidding or OZI forbidding.
I'm in terms of glue balls from the JPSI, or I mean, that's supposed to be a good way to produce glue balls, although I don't think we produce enough JPSIs and GLuEX to make that a viable production mechanism. Very low, you need millions of events really to be competitive in the glue ball market. And And in general, in principle, you could say photo production might be interesting as well, but it's not traditionally considered one of the glue-rich channels for producing pure gluonic final states. It was interesting for the hybrid mesons where you can excite the gluonic degree of freedom. Not to say that there aren't people interested in looking for it. In fact, one of our students here at Carnegie Mellon is looking at what would be considered a glue ball final state.